Welcome to webinar number 432, and yes, you guessed it, I am drinking structured water using liposomes, infrared light, 660 and 620. Gerald Pollack is jealous. Fourth phase. All right, so why are we here besides fourth phase water? We're here for NAD Gold, and what's NAD Gold? That's our new liposomal delivery of NMN, not NR, NMN, nicotinamide mononucleotide with trimethylglycine. So they're always exciting, but this is the game changer. This was such a game changer for me, and I'll tell you some stories of some of the game changing that I've seen along the way while we use this product. And so NAD has been the hot topic all over anti-aging medicine, integrative medicine. Everybody knows now we need high NAD levels to tie everything together. You know, and through all the time in anti-aging medicine, everybody talks about, oh, well, this goes down with time, we'll supplement it, we'll be all better. So glutathione goes down with age, put that back in and you're all better. Now, we know that liposomal glutathione helps a lot, but it doesn't totally reverse the clock. DHEA goes down with time, put some more in, no good, and I'm getting man boobs because I'm turning that all into estrogen. Like something is missing here. Finally, we get something that seems to underpin everything else, and that's NAD. So we're going to go through, we're going to talk about how NAD affects aging, how NAD goes down with time and what effects that has, and then how do we raise those levels up, and how do we blend that with other things? I mean, it's funny, you know, a couple of years ago, everything was about methylation and MTHFR, and oh, I'm an MTHFR. We all know what we said when we had an MTHFR. SNP, and I was like, oh, well, then I got to put a lot more methyl groups. And what's the antidote to methyl groups? What is the devil of MTHFR? But vitamin B3. Nicotinamides, never get nicotinamides near you, or you will demethylate everything and you will die. Well, how far we've come. Here we are advocating B3, but how are we advocating B3? In balance with methylation groups, and we'll see why. And all of a sudden, poof, you got yin and yang both together, you got them all balanced, and now we get really nice energetic activity. We got a great coupling of the mitochondria with the nucleus and activation of the golden goose, the sirtuins, and other things that go with that. We get all, you know, hyper-focused on sirtuins, but there's FOXOs, and there's a lot of other longevity genes. So this is going to tie together a lot of the work that we did with keto B46 around AMPK activation and with the liver sauce around AMPK activation. We see how AMPK activation brings this clarity to the metabolism, where you're not just storing calories and building on mass, but you're burning cleanly. So that was a beautiful story. And with that story of the AMPK activation came sirtuin activation. And with that, with AMPK activation came a building of NAD levels, a shifting of NAD plus versus NADH, and with that activation of sirtuins and other longevity genes. But what we're going to find along the way here is, even if you do all the AMPK activation, if you don't have adequate sirtuins, either because in age your enzymes for generating NAD are low, or there's something drawing off NAD. If you don't have adequate NAD levels, you can't actually get everything to happen. You can't activate the sirtuins. So when we're using AMPK activation to generate mitochondrial biogenesis, we only get halfway there unless we have enough NAD. So NAD really is the missing link. And it turns out that the less NAD you have, the less NAD you get, which brings me to, oh, hold on, the Bible, where I always go. As I said on stage at A4M, what is this slightly hedonistic tantric Buddhist talking about the Bible for? I'm talking about the Matthew effect. So the Matthew effect says, it derives from the quote from Matthew 25:29. It was also earlier in Matthew. You'll find it in Luke. You'll find it in Mark. And it says, to those who have shall be given more, and they shall have abundance. For those who have not, or from those who have not, shall be taken the very last bit they have. Now, I've always loved this quote because, you know, it's a very spiritual quote. As you get into meditation, as you get into contemplation, it just sort of grows on you and you get more and more and more. And as you get away from it, what they call the fall from grace, you get less and less and less, and you get more and more cynical until you're, you know, in that hole in the gutter over there. But it turns out that a lot of biochemical processes are the same way. And I see this again and again, but I've never seen it so much as with NAD, because as NAD grows, processes that build NAD grow. And as NAD goes down, processes that build NAD go down. And you're left a dried up, shriveled up little prick. So where does NAD fit into our life? Well, it turns out that it fits in just about everywhere. And we'll see a couple of figures come up through this, some of the heroes of the NAD. One of them is David Sinclair, and he's probably the most prominent. But then there is, in his lineage, his academic lineage, his father, academic father, Leonard Guarente. You'll also see a Frenchman, maybe he's Belgian, Johan Auwerks. And there's a Japanese guy, and of course I can't remember his name right now because it's not like David or Leonard. And so we'll hit on that later, and we'll bring him up because he is the hero at the end of this, is because he's the one who says, let it be known, NMN is on the table and you do not need nitrogen. And so you notice he says that in a very Baptist, like preacher-like voice, which is funny for a Japanese guy. But he is the one who's given us the light at the end of the tunnel, and that is the transporter that brings the NMN in. So no longer does that story that NMN is too big to be absorbed, it can't get into the cell. That was all bullshit. So what does NAD do for us? It does just about everything. So we can see that, we're having a lot of fun here. I mean, this is clearly a fun one. This is the coming of age of, oh, no, let's not use that one. Let me get myself a good pointer here. Laser, red laser, all right. Oh, I don't have no red laser. Oh, yeah. Give me one more second. Laser pointer. Yeah, all right. So one of the things that NAD is most known for is mitochondrial function and metabolism. And the next thing that you'll hear the most often are redox reactions. Wow, redox reactions. I had a woman come up to me once and say, now I know the key to health. We have to have more redox. Just bring up those redox. And I'm like, that's not a thing, you know. That's reduction, oxidation. One thing's oxidized, one thing's reduced. There's a sharing of electrons. You flip things around. There's no such thing as a redox level in you. But at the same time, she was right. We need to have a lot of oxidation and a lot of reduction, and we never want to get muddied into the middle where they come together, because these are yin and yang. You need to preserve both of them, and we'll see in the NAD story that there is a yin and a yang. There is oxidized NAD+, which is being reduced to NADH, and in doing so is oxidizing carbon substrates. It's taking electrons away from them. The reduced NADH is going into the oxidative phosphorylation cycle and making ATP. So we need that prominently oxidized so it can oxidize the carbon substrates coming into it. But then it has this sister here, and I'm making the sister the reduced one. This is my sexist plea here, because it's a more negative one. This one carries excess electrons and donates them to your oxidized inner antioxidants. And so that's NADPH. So that's driving reductive metabolism, while NAD is driving oxidative metabolism. But they're coming from the same pool of NAD, and they get diminished together. And so what you'll see when you're young and healthy, you've got a strong oxidized pool and a strong reduced pool. And as you get older and weaker, the oxidized pool gets more reduced, and the reduced pool gets more oxidized, and you're coming into that muddy gray middle, where we really want black and white always existing amongst each other. That's what the Tao says. You know, you want them mixing, but never blending completely, because thus they obliterate each other. So there's our philosophical redox discussion. But then we get into other things, circadian rhythm. The mind blower there, and I've seen it with a number of my friends that have sleep trackers, is you sleep less, but you sleep deeper when you're on NAD. My deep sleep cycles went from practically non-existent, and thus I needed a lot of light sleep, into really, 1 to 2 hours a night of deep sleep, whereas I used to get 10 minutes. And that was just from bringing on NAD, and a lot of other people confirmed that for me. Inflammation, and it's not, oh, it's anti-inflammatory. It's controlling, it's creating proper inflammation. One of the things you see as you build up the NAD pools is this sort of zippering up of your adrenals, your immune system, I'm pointing at my thymus here, and your energy. And so you'll find that you have a lot less brain fog as your adrenals rise to the occasion to control proper histamine reactions, proper inflammatory reactions, and keeping everything compartmentalized as opposed to it all bleeding together. DNA repair, it feeds into DNA repair. And that's one of the ways you bleed off NAD as you get older. You're exposed to all this radiation, all this toxicity, all these different factors that are damaging your DNA, and NAD is getting sucked into there to the repair of the DNA, and you need to replenish your pool of NAD. Cell division, cell signaling, the epigenetic aspect, very, very big aspect. And in fact, this is part of why you need to pour in the methyl groups, is as you activate NAD to go in and repair your genome and edit your genome, you're going to be using methyl groups. Now we're going to find that that's not the main reason you need the methylation groups. It's probably the secondary, second most important reason to bring in the methyl groups. The other is to continue the metabolism of NAD. So NAD is using methyl groups. It's using it in epigenetic activity, and it's using it by its own metabolism. And that's why you have to pour them in. In the methylation thing, the MTHFR, it was like they were in some war and this demon B3 was killing your methyl groups. No, it's sucking them into use in your body, and it's using them as you metabolize out the nicotinamide that's generated from NAD. So it's just you need to pour them in together. So normally you'll see these kind of things like NAD is generated, or healthy NAD plus levels. And this goes into that redox couple, the oxidized NAD, the reduced NADH. You need dominantly oxidized NAD. And exercise is driving that, diet is driving that, and NAD boosters are driving that. And so what are NAD boosters? We'll see various forms of B3 are NAD boosters, but we're going to find that our most special NAD boosters are nicotinamide mononucleotide and nicotinamide riboside. And then NAD, you have it driving in brain, nervous system, liver, vasculature, heart, lymphoid tissue, reproductive organs, kidney, pancreas, muscle, and adipose tissue. And back to the AMPK, a lot of this is driving a nice, clean, healthy metabolism. Now, what we see between youth and aging, or between health and disease, is this switching of the NAD pools. And so we want to keep the NAD levels up. And so here you have calorie restriction and exercise driving NAD levels up. The opposite of that, which is driving them down, would be a high, here they have high fat, high sugar diet. It's when those come together. It's not just when you have high fat, because high fat diets, we see, as long as you keep the carbs low, keep you burning super clean. They are AMPK activators. So it's really the high sugar and sedentary lifestyle. So all those are driving towards insulin resistance, fat storage, all of the risk factors for health, whereas high NAD, and here they have AMP activation, or AMP elevation, which is driving AMPK activation, all moving in the direction of health, activating AMPK, activating sirtuins, blocking mTOR, and here they have some of the things coming in that work as pharmaceuticals to do that, being metformin or rapamycin. Now, we see in our Keto Before-6, we can bring together nutraceuticals that are AMPK activators and mTOR blockers, and so we're going to talk how to blend together at the end. How are we going to blend together NAD Gold with methylation factors and either sirtuin activators or AMPK activators, or a combination of those two. But when you have all of those things moving quickly, then you're moving towards the youthful disease-free state. So this is just more, this is from the Sinclair world, and it's showing more of the different genes that are activated in each one of these elements. So when you're leaving brain health, you're downregulating NF-κB, upregulating phoxogenes, some of the ones that come up here in muscle. PGC1 alpha. PGC1 alpha drives mitochondrial biogenesis. And so as we get deeper into how NAD works with energy generation, especially in the mitochondria, we're going to talk about mitochondrial biogenesis, and we're going to talk about nuclear mitochondrial coupling, the way the nucleus and the mitochondria work together and send signals in to drive the oxidative phosphorylation cycle. And we'll see with age, the signals from the two of these get dysregulated. It's like when your mom and your dad are giving you different signals, and there ends up being a little bit of trouble. And so one of the ways that we increase mitochondrial activity is through PGC1 alpha, which makes more mitochondria. But then they found that there was a whole different way that NAD and sirtuins work into that relationship between the nucleus and the mitochondria, and it's a PGC1 alpha independent way. And so if we look at the pathways for formation of NAD, this one here in the middle is probably the most important, and this is called the salvage pathway. In the next couple of slides, we'll look at the different ways that we generate NAD, but then NAD, when it's used, creates nicotinamide. And nicotinamide then needs to be driven back into nicotinamide mononucleotide, or NMN, and that needs to be driven back into NAD. And we'll see that where things break down is with the regeneration of NAM, nicotinamide, into NMN. There is an enzyme, NAMPT, which easily gets blocked, and it leads to a buildup of nicotinamide and a deficiency of nicotinamide mononucleotide. Now, let's see what the next slide is. Now we'll go back to that. One of the problems with this is that nicotinamide itself blocks sirtuins. So we'll go back deeper into this slide a little bit later. We'll see that NAD drives the turnover of the sirtuin and leaves NAM, which then is a negative feedback inhibitor of sirtuin. So you need to get rid of the NAM. And that's either through regenerating it or methylating it and bleeding it off. And that's the key to why you need the methylation. So here we have more. This is from, there's the Japanese guy, Shinichiro Imai. Can't believe I forgot his name. How could I not know that? All right. And Leonard Guarente, that's, you know, white name, you can remember that. So here they're going in the same thing, NAD and sirtuins in aging and longevity control. In fact, that'll come up a little bit later, that all these guys recommend to take NAD precursors and sirtuin activators together. And so in the Guarente group, because he's part of an MLM that sells a combination of NR and pterostilbene, he recommends that. Whereas Sinclair, his academic child, is not part of any of those, and he agrees with us, and he uses NMN and resveratrol. But resveratrol and pterostilbene are like the same thing, and NMN and NR are very similar as well. All right, and so here they have caloric restriction, exercise, and stress leading to increases in NAMPT, but a little while later we'll see what on the same slide, we'll see what decreases NAMPT: degenerative conditions, ischemia, inflammation, and aging. And so we don't have to rely on NAMPT, which is more it's more reactive to the different things that can come in and block it. We can come in from the side with NR or NMN. Now, what you'll see in all of these is nicotinamide riboside becomes nicotinamide mononucleotide, and that directly becomes NAD. So NMN is the most direct precursor to NAD, and then we have that driving sirtuins and decreasing aging and increasing longevity. As we go down farther, we'll look at this complicated diagram here, and it has a decrease in NAD leading to a decrease in sirtuins, and you'll see two pathways, TFAM being brought down, and TFAM is your communication driver between the nucleus and the mitochondria. And we have also coming down PGC1 alpha, which drives the synthesis or biogenesis of new mitochondria. But PGC1 alpha is dependent on AMPK, and the TFAM pathway is not. So basically, if you are in a fasting state or carb restricted state, you're going to drive the PGC1A path. And if you're not, if you're eating carbs, then you're going to rely on this TFAM path. So NAD is drawn down in the body, one, through a decrease in NAMPT activity, and also through an increase in the NAD consumers. So the NAD consumers are using NAD to, one, to fix genetic damage. So that means excess EMF and radiation exposure are going to draw down NAD. This is one of the first introductions I've had to NAD, is that NAD precursors and AMPK activators were making me much more resilient to flying. And what do you get during flying? Nothing but EMF and radiation. And it was just stunning. And I got to PaluFX, and Joe Mercola ran over to me and he's like, Chris, I got to tell you. You know, and it was about Martin Paul's recent research on how EMF dysregulates calcium channel transporters and creates calcium excess in the cell. And the thing you need to fix that is NAD. So EMF is drawing off our NAD levels, and toxins creating DNA damage, drawing off our NAD levels. Now, another thing we're going to see is CD38 activity. CD38 uses NAD to fix tight junctions. So anything that's creating weak tight junctions is going to need NAD to fix it. We're going to see this whole overlap in fixing leaky gut by AMPK activation and Sirtuin activation, and ultimately all through high NAD levels. So here are two pathways. There's the TFAM pathway and there's the PGC1 alpha pathway. And we're going to get to some pictures of nucleus, mitochondria, oxidative phosphorylation, and the two different ways that they can come in to fix mitochondrial activity. All right, now another thing that came from that was some of the reasoning behind how it fixes circadian rhythms. I remember when I was interviewed by Sim Land, and he was asking me, oh, what about circadian rhythms and this? And I thought he was saying that there's a circadian rhythm of NAD production, which it probably is. It's probably a little higher in the morning. I don't see that so much, but we see it fixing circadian rhythms. It makes you awake during the day and deeply asleep at night. And what's better than that? And part of the Sirtuin activity is activating the clock genes, which are driving our circadian rhythms. And they're interacting with the Sirtuins. The Sirtuins are activated by NAD. All right. So summary: we've got cardiometabolic health controlled by NAD levels. We've got energy through ATP production in the mitochondria driven by NAD. We've got cognitive health driven by NAD. We've got immune health controlled largely by NAD, liver health by NAD through AMPK activation and its activity in turning up lipolysis, breakdown of fatty accumulation in the liver, tight junctions in the liver, one of my favorite terms, leaky liver. You get into one of my other podcasts, we get into other leaky organs, but we won't get there now. We'll stay with leaky liver. Membrane polarity and barrier function integrity, which is back to this leaky liver, leaky gut. Membrane polarity, remember the cell membrane needs a polarization. It's got a charge differential between the two sides. The membrane is a capacitor, and in that charge separation, it's driving a lot of the enzymatic activity that's held in the membrane. Detoxification and free radical control. Where does that come from? That's not coming from sirtuins. That's not coming from mitochondria. That's coming from the sister of NAD, NADPH, because that's what's driving reductive metabolism. Like say you're using glutathione to quench a free radical, you've just oxidized the glutathione and you've got GSSG and you've got to drive two hydrides back onto that. Those hydrides come from NADPH. So NADP we want in the reduced form, NAD in the oxidized form, and then inflammatory control. Like I said, you'll see that when you bring up your NAD levels, it's going to zip up this axis between your brain, your immune function, and your adrenals, and as an extension of that, or maybe a mediator of that, your mitochondria. And you'll find that fogginess that you have after eating certain foods will just disappear, and you'll just be able to eat, feel better, and have energy after. I mean, it was a total game changer for me in how it controlled all of that. So our pathways. So there is a couple different pathways for getting. Let's count them. So there's 1, 2, 3. Essentially 4 pathways. There's 3 traditional pathways. There's de novo synthesis. So it's essential you will die without NAD. But where are you gonna, usually we're thinking that's a nicotinic acid derivative. And so where are you gonna get B3? Now you can eat raw liver, you're gonna eat raw organs, you get a lot of B3 in there, but you're not always exposed to that. Well, it turns out you can make it from tryptophan. So that's the de novo biosynthesis, taking it from amino acids, driving it into quinolinic acid, and then dumping it into the price handler pathway. So the price handler pathway is how you take niacin, nicotinic acid, into NAD. The de novo synthesis dumps into the price handler pathway, and then probably the most important is the recycling pathway. Now, the recycling pathway is taking nicotinamide and regenerating it through NAMPT into NMN and then back into NAD. So key here is when NAD is consumed by sirtuins, it produces nicotinamide. When it's consumed by PARPs, these are the poly-ADP ribose polymerases, it's turned back into nicotinamide. When it's used by CD157 or CD38, it's turned back into nicotinamide, and it needs to be recycled. Remember again that nicotinamide also then blocks those pathways when it pools up. So that's a really crucial one, is to keep your internal paths going, but the NADPH enzyme is what goes down with age. So here we can see it nice and clearly. If we go up here, so we've got a gene and we want to deacetylate it. Remember, the sirtuins are the deacetylases. So acetyl groups on a gene are like silencers on a gene. And we'll see later when we look at PGC1A activation, there's first phosphorylation of it, which activates it, and then there's taking the acetyl group off, the silencer off. So when there's an acetyl group, a silencer on the gene, you need a sirtuin to go, and NAD first links on to the sirtuin and drives the deacetylation. Now, if we look over here in this one, NAM is produced after the NAD catalyzes the deacetylation. And then it sticks onto the sirtuin and prevents the docking of a new NAD. So NAM is produced and self-modulates sirtuin activity and blocks it. So you need to move that back out to NAD, or you need to move it away through a methylation path in order for that sirtuin to be reactivated. Now, what's this other thing that we have here? A stack. If we look all the way to the right, we've got NAD and we've got a stack. That's a sirtuin activating compound like resveratrol or pterostilbene or quercetin. So when you have the sirtuin activating compound and the NAD together, that's when you get the super activation of the sirtuin. Now you can have the stack on there, you can have resveratrol, but if you don't have the NAD, you can't activate the sirtuin. So NAD alone activates the sirtuin, resveratrol alone does not. NAD plus resveratrol activates it doubly. So that's what we want, and that's why there's this recommendation to take NAD precursors and sirtuin activators together. And the enzyme that drives NNMT out, or I'm sorry, the enzyme that drives the NAM out is called NNMT, nicotinamide something methyltransferase. I remember all these names. And we'll see that certain pathologies hyperactivate that and drive down methyl groups. So there's a really cool anthropological paper later, like Diet and Anthropology, about balancing of nicotinamide sources in the diet and methyl sources in the diet. And if you have too much nicotinamide and not enough methyl, that creates a pathology. If you have not enough nicotinamide and too much methyl, that creates a pathology too. So you need to balance the two. All right, here's one from Johan Auwerks, NAD metabolism and control of energy homeostasis, stasis, a balancing act between mitochondria and the nucleus. And so we see all of this activity. We see, now this was done back in the days where they weren't sure NMN goes in. So they have NMN with a dotted line in, like, we think it probably goes in because Sinclair keeps doing animal studies with NMN and they work, but we've only found the NR transporter. So we'll say NMN becomes NR and transports in. So that was the old Niagen story, is that NR is the only thing that can be trafficked cell to cell and NMN can't. Well, now we know that's not true. All right, so we have NR going in, we have it becoming NMN again, we have it going into the nucleus where it activates sirtuins and PARPs, we have it going into the mitochondria where it's activating sirtuins there. And we'll find that there's this elaborate dance between the nucleus and the mitochondria, and the correct communication from them is essential, and it's driven through sirtuin activation. All right, so we know NAD is crucial. It's involved in every system in our body. It's how we generate energy. It's how we tie things together. So how is this loss in aging work? So we said we have a decreased synthesis from the NAMPT enzyme, and that's decreasing the formation of NAD from NAM, nicotinamide. So it's blocking the salvage pathway. And aging, inflammation, ischemia, degenerative conditions all block this. I mean, first NAD was just about aging, and now they're finding it's about so many different chronic disease states too. So yeah, inflammation blocks it, but you know, I found some papers on mold toxins where they're blocking transcription of the enzymes to form NAD. And you find this in mold toxicity and NAD, or in mercury toxicity, that there's problems in energy generation, Lyme disease, serious energy generation problems. And then later on, we're going to get into talking about NADPH and mercury toxicity, and we're going to see what toxins do to NAD levels. And that's also, there's less formation, and there's increased consumption of NAD through the PARPs, which are gene repair mechanisms. CD38 is repairing tight junctions, and SARMs are repairing something that I forgot about. So we'll just forget about that for now. Now, with age, we also have a decompartmentalization. All right, so this is one of the studies that was looking at the human brain. Over age, you'll see a couple things going on. So total NAD is the green, and you see that going down, but it's not going down super radically. What's changing even more, and you'll see other parts of the body. I think the brain is kept at higher levels, and I've seen, I don't have them in here, but I've seen other studies where the NAD levels in other organs are much more precipitously declining. But the total thing isn't the whole problem. The fact that the oxidized is going down and the reduced is going up while the total is going down is the real problem. And having a serious excess of oxidized over reduced is the real driver. And when they look at total NAD, there's a lot of NAD bound into proteins. And you'll see the ratio of oxidized to reduced is like 7 to 1. But free NAD circulating through the system, the ratio of oxidized to reduced is more like 700 to 1. So it's a really crucial driver. And when that ratio goes down and it becomes more reduced, it stops activating sirtuins. So this ratio between the two is measured in the redox potential. And you see these negative numbers over here from negative 290 to negative 310. In this case, where we want more oxidized than reduced, we want to be higher up the scale, a less negative number. And so with young age, we're around 295, and then we go down to 305 over time. So it's becoming increasingly more reduced, which is offering less oxidative potential and thus a lower metabolic rate. All right, and you'll see this in a bunch of different papers. Bad diet, sedentary lifestyle, all blocking NAD, whereas NR and NMN can come right in and cheat the whole system and activate your sirtuins. Whereas your normal ways that you're going to drive this are with exercise and caloric restriction. Now here you see caloric restriction leading to AMPK activation. Well, exercise also doing that, leading to AMPK activation and leading to higher NAD levels. But again, that model where that's all you need to do to activate all this only works in a younger, less stressed system where there's adequate NAD. When you get older and the NAD levels go down, the AMP does, even if you activate AMPK, it does not cascade all the way through the system. One of the interesting things that you'll find is a lot of the mitochondrial activity or the mitochondrial health is driven by this UPRMT. That's the mitochondrial unfolded protein response. And the unfolded protein response is the cleaning up in the mitochondria of poorly folded proteins. What does that mean? Well, we're making proteins all the time, and proteins are a very complex three-dimensional structure, and they involve all of these sulfur-sulfur bonds and hydrogen bonding to fold into a shape that has catalytic activity. And when you have a misfolded one, it doesn't work, but it builds up in your cell. And so you need this point at which you go and you clear all of that toxic protein out. So that is an endogenously produced toxin that needs to be moved out. And that's one of the things that sirtuin activation does. All right, so NAD is going down with time. It's going down with different pathologies. It's affecting all the energetics in the system, but we can fix this. And what happens when we fix this is we fix all of these metabolic problems. And so this is one of the classic papers on long-term administration of NMN, nicotinamide mononucleotide, mitigating age-associated physiological declines in the mice. So with age, in the controls, they're getting fatter. In the NMN treatment, they're not. In the controls, they're decreasing their energy metabolism. In NMN supplementation, they're not. Insulin sensitivity is going down, insulin resistance is going up in the controls. That's not happening. You're increasing insulin sensitivity and you're getting more pure lipid metabolism. You've got gene expression changes that are changing with age, but not with the NMN. Mitochondrial problem changing with age in the control, not with the NMN. Eye function, bone density. All of these changes, all these declines with age are not happening when you supplement the mice with the NMN. All right, now let's go into the core of where all this is happening. Because yeah, and NAD levels, they're signaling cell to cell, organ to organ, but the meat of the activity is in oxidative metabolism in the mitochondria. And so in the Krebs cycle, you're feeding in acetyl-CoA and you're oxidizing these carbon substrates, and NAD is pulling electrons off of them and turning into NADH. So at these three parts, that's happening. Then what happens? The NADH is transported into the inner membrane space of the mitochondria, and inside the mitochondria, it is going through oxidative phosphorylation, where the electrons are donated into the electron transport chain, and the proton that is taken off, so NADH has excess electrons and a proton, the proton is pumped out, creating that proton gradient, and that proton gradient is eventually relieved by driving through ATP synthase and creating ATP. All right, so that's the core of it, and this system over here is called oxidative phosphorylation. Now, in the theories of aging, there has been a lot of mitochondrial stuff, and originally it was a free radical theory of aging, and it eventually evolved into a mitochondrial theory of aging. They saw that this was core in the mitochondria. It wasn't just free radical exposure throughout the body. It's just something going on in the mitochondria. And they found that there was increased electron transport system decoupling in the mitochondria, where the electrons are not handed subunit to subunit to subunit. The protons are not pumped out. They're not coming back in, creating ATP. Instead, there's like a miss of the baton handoff, and the electrons fly off as free radicals. And this is increasing in the mitochondria, reactive oxygen species, and there's a decreased antioxidant capacity. All of those are leading to increased mitochondrial damage and decreased mitochondrial mass. So each cell has less mitochondria working for it. All right, so first look at the electron transport system decoupling. So this is pretty cool. So the mitochondria have DNA in them, right? And of course, the nucleus has DNA in them, and we know that, but we don't realize always how much of the mitochondrial DNA is used to generate proteins in our system. And it turns out there's a lot of different subunits in oxidative phosphorylation, and 13 of them are encoded by mitochondrial DNA. And the rest, and I don't know that number of what the rest is, are encoded by nuclear DNA. And they have to be transcribed and built at a stoichiometric proportion, meaning there's an exact number coming from the mitochondria and it's balanced by an exact number coming from the nucleus. And when that happens, then the electron transport chain works. But what if you're missing one of these subunits because the mitochondria is not doing its job? Then you're going to have electron transport system decoupling, and you're going to have that free radical formation. So it turns out, yes, with age, there is a nuclear mitochondrial protein imbalance. And it is always that the mitochondria are not making enough of the subunits, and there's a non-stoichiometric transcription of oxidative phosphorylation subunits, creating decoupling of the electron transport chain and creating reactive oxygen species. Now, you've heard of like oxidative bursts, respiratory oxygen bursts, and there's increased ROS generated during these bursts of activity. And you have this nice system in there of free radical control in the nucleus for containing all that. In fact, I'm sorry, in the mitochondria for containing all that. In fact, in the mitochondria is more reduced than the rest of the system around it, which is interesting because you think of all this oxidative activity going on in there, but there's actually more reducing equivalents inside the mitochondria to deal with all of this. So the first of our ways that NAD levels help restore mitochondrial activity is through bringing a balance to the force. The light, the dark, no, I'm sorry, I just watched Star Wars. It's through bringing a balance between the nucleus and the mitochondria. Now, remember this diagram from before, there's this thing TFAM. And when TFAM is activated, it sends signals into the mitochondria to increase the mitochondrial gene expression. And so that's the messenger that goes to the mitochondria, ensures they're on the same page. So TFAM gets them working together. This is a PGC1A independent pathway for sirtuins to increase oxidative phosphorylation. All right, and part of what comes with this is the unfolded protein response and an increase in expression of superoxide dismutase. All right, now I got this. All right, let's look at this one first, and I got to go back one. So the first one was increased electron transport decoupling, creating problems. And the second thing feeding into the problems was a decreased antioxidant capacity. There's lowered glutathione, glutathione peroxidase, and superoxide dismutase, and catalase activity. And okay, no, we are fine. All right, we'll get to that in a second. I decoupled myself. All right, two ways that sirtuins are acting on the mitochondria. The one is the PGC1 independent pathway that's getting them to make stoichiometrically balanced oxidative phosphorylation. The second one is the PGC1A pathway, which leads to mitochondrial biogenesis. So now you see there's 3 mitochondria. So PGC1A is generating more mitochondria, but PGC1A is AMPK dependent. So when AMPK activation happens and Sirtuin activation happens, you get mitochondrial biogenesis. Remember, AMPK activation, we'll go back to it in a little bit, but for the keto before 6 work, AMPK activation is achieved through fasting, through carbohydrate restriction, through diet, and through nutraceuticals like berberine, resveratrol, quercetin. So when those 2 are together, you get mitochondrial biogenesis. If you're eating carbs, then you just get this PGC1A independent TFAM pathway balancing nucleus and mitochondria. All right, next piece of our puzzle here is antioxidant capacity. So here's where we see the other side of NAD, and that's NADPH. Sorry, I got a blurry one here, but there's this balance between NAD and NADPH. So NAD is moving over into NADP, and there is this drive between putting hydrogens on to NADP to make NADPH, and then them donating the hydrides to glutathione through the activity of glutathione reductase onto thyroidoxin through the activity of thyroidoxin reductase. So glutathione, thyroidoxin, ascorbate, all these are antioxidants that are contributing to free radical control, and they're donating electrons in those cases and oxidizing themselves, and they need to be re-reduced to brought into this dominantly reduced pool. So glutathione is 99% reduced and a little bit oxidized. And every time you oxidize one, you need to drive it back into the reduced pool, and you're using NADPH to do that. So NADPH is driving reductive metabolism, whereas NAD is driving oxidative metabolism. And in all these pools, you have to keep the right ratio. So when the ratio of reduced to oxidized glutathione starts changing to more oxidized glutathione, there's a whole bunch of genes that will turn off because they see that they're under a stress environment and they can't drive forward, so they shut off. And a lot of these are longevity genes and longevity proteins, all right? So what you find with age, and here this is in aging mice, and this is an Alzheimer's disease mouse neuron line, and they're showing that in these, what they did is they developed out this mouse that develops Alzheimer's real early, and then they start studying it. One of the things that they found in it is that it's with age, its NADPH levels go way, way down. And when they go way, way down, the reactive oxygen species go way up, and the glutathione goes way down. And so if we're to track, we have these 2 mice. So with the white, the hollow symbols here, that's the regular mouse. And as it ages, it's going into middle age, it's getting more and more NADPH, and then it kind of trails off with time. But the Alzheimer's prone mouse has a lower level of NADH. It never developed, they all started the same, but it never develops a full reductive system, and it goes way down with age. And this redox ratio of NADPH to FAD is how they measure the redox potential. The higher that is, the more reducing equivalence the NADPH has. And you see in the Alzheimer's transgenic mouse, it just goes down, down, down with time. And now you see these things flip. The white lines are the normal mouse. And yeah, reactive oxygen goes up with time, but it goes way up in the Alzheimer's, the Alzheimer's prone mouse. And with glutathione levels, you see glutathione levels stay down when NADPH is low. So remember, and they could probably go back to this and see that there's low NAD levels in these as well. So as NAD levels go down, NADPH goes down, and ability to deal with oxidative stress goes down. And in these, when this is just more of the same, now I forget what they did in this one. Oh yeah, they treated these with nicotinamide. All right, so if you go over to the right, this is the regular mouse, the Alzheimer's prone mouse at 8 weeks old. You see the glutathione levels as this thing ages are lower. But if you supplement both of them with NAD or NAD precursors, in this case nicotinamide, the glutathione level in the transgenic mouse goes up to normal levels. Whereas the regular mouse, it doesn't really change because he's already got a good NAD level, which gives him a good NADPH level, which gives him a good glutathione level. So we see here, not only does NAD supplementation increase metabolic efficiency, it's increasing reductive efficiency as well. And this is a different mouse paper, and this is looking at neurons of rats. Now, remember, with age, the NAD to NADH couple changes and gets more reduced. Now, when we look at the NADPH couple, this is middle-aged versus old, it's getting more oxidized. So the thing that we want oxidized is getting more reduced with age. And the thing that we want reduced is getting more oxidized with age. They're getting into that muddy gray area. And so over here, looking at the redox potential, we want it nice and reduced. This is embryonic, middle-aged, and old neurons. You see it going down with time. But then, if you bring in high glutamate levels, it becomes more and more oxidized. It becomes pathologically oxidized. And you see, if you look through, all the teachings we've done over time, we look to glutamate quite often. We're looking at glutamate excess as a pathology with excess of mercury, because mercury stimulates activity of the glutamate receptors, which creates free radical activity and creates damage in the brain. We see neuroinflammation is associated with increased glutamate activity, decreased GABA activity, and we use CBD to normalize those because of that neuroinflammation, because glutamate excess is creating more and more free radical activity in the brain. So what do we need to balance that? I mean, yeah, we use things like CBD and GABA to try and balance that, but we need adequate NAD levels to make adequate NADP levels to create free radical control by keeping reduced glutathione, keeping reduced thyroidoxin, and keeping reduced vitamin C. Now, let's look at NAD in the detox system. Where are we? Got 1 hour into this. I'm halfway through. I'll speed up. All right. NAD, glutathione, and mercury toxicity. So this is very cool. I saw this paper, or I saw Michael Oshner speak on this at IOMT probably 5 years ago, and he was giving this lecture to all these dentists. They had no idea what he was talking about, and I was like, oh, this is so cool, right? And in it, we'll see in some of these, he was creating damage with methylmercury, and he found he could reverse it with NAD. And why is that? Well, it's because NAD fixed the glutathione system. So it fixed the resistance to the mercury. So whenever I talk about mercury and toxicity, you've got susceptibility and resistance. Resistance is an elevated glutathione system. So here, now let's see what happens with mercury. And here we've got this RFU is a activity of mitochondria, and the 0, 10, 20 are doses of methylmercury. And so he was using C. elegans, which is this little worm that's good to do biochemistry experiments on. All right, and so with no treatment, you give them more and more methylmercury, the fluorescence of the mitochondria is going down, the relative mitochondria copy number, so you're getting less mitochondria. So NAD is blocking mitochondrial activity. It's actually blocking how many mitochondria you have, probably by blocking mitochondrial biogenesis. So there we see that the toxin directly is killing mitochondria. But if he pre-treats them with NAD, and he did direct pre-treatment with NAD, which is easy with these little worm creatures, now the mercury doesn't have that effect on the mitochondria. So it's protecting the mitochondria. And we look a little bit deeper into this. So here, now this is interesting. Back to those who have shall be given more, and those who have not. very last bit will be taken away. So NAD levels with treatment of methylmercury, what does it do? They go way down. So methylmercury is sucking down the NAD. The low NAD levels are blocking the sirtuins from making more mitochondria. The mitochondria are going down. So it's a downhill battle. Now, if he keeps enough NAD in the system by pre-treating it, so NAD can be consumed by the toxin, but there's still enough to keep everything going. What happens to NAD levels at a higher mercury level is they actually go up. That's pretty crazy. Now, mercury has a hormetic response. Mercury, arsenic, they're NRF2 activators. They can activate the system to save the body, but if the toxicity gets too far, the system just crumbles. When we keep the NAD levels up high enough, the hormetic response comes all the way through, and the NAD levels actually go up. The capacity to have higher NAD, and we'll see in a second, higher reductive capacity comes all the way through. So this is one of the the mysteries to some in the toxin world. It's like if you take a totally healthy organism and you expose them to toxins, they usually just get stronger. But then you take a weakened organism and you expose them to the toxins, they just crash. And so there was a guy running the circuit talking about the hormetic response, and he was like, oh, look how good PCBs are for you. Look how good arsenic is for you. And what do they used to give, as a tonic back in the way old days? They give arsenic because it is an NRF2 upregulator. But at a certain point, it just crashes the whole system out. So if you don't have the resources to deal with it and rise to the challenge, it just crashes you out. So now I don't remember what these little colors were. All right, there's the methylmercury, blah, blah, blah. All right, fused. Here we go. So glutathione levels here over on the right as, oh yeah, all right. So the red was reactive oxygen species. And as you go with more and more methylmercury, you get more and more reactive oxygen species staining red in this little worm. And then as you add the NAD on, that red goes away because you're able to deal with it. If you look over here at the glutathione levels, so the methylmercury goes in, glutathione's it's dealing with the methylmercury by complexing to it and leaving the system. So you're draining glutathione out of the system. And as you drain those levels down, the body can't deal with the methylmercury anymore and the toxicity sets in. But if you pre-treat them with NAD, they can keep regenerating the glutathione levels and they can handle the insult. I mean, this is so fundamental. It's one thing to chase with, oh, I'm going to chase with C here, I'm going to chase with D there, I'm going to chase with glutathione here. But NAD is the one thing underpinning everything and enabling you to handle more and more. All right, so clearly we want to raise NAD. We're going to be raising oxidative metabolism. We're going to raising reductive and free radical and toxin control metabolism. And how are we going to do that? All right, so we'll talk a little bit about AMPK activation because AMPK activation leads to changes in NAD plus and NADH ratios, and it leads to changes in NAD synthesis, and it leads hopefully to Sirtuin activation. Then we'll talk about precursors. Now we've got our Cadillac, or rather our Maserati precursors, the NMN and the NR. It's called the NR a BMW because I beat one in a drag race today. That was pretty good. M3 against the Ghibli. Ghibli wins. I probably shouldn't say that. There's police listening.
It's on a close course.
It was on a closed course right around the technology park here. And then we have the cheaper ones, NAM, NA. So what's NAM? That's nicotinamide, and NA is nicotinic acid or niacin. So those are your typical B3s. And then you got your high-end B3s, the NMN and NR. And so NAM and NA will get you up. I mean, that's dietarily how you keep these levels up. But as you get older, you'll see you can't really keep up and keep those levels high, even if you're taking regular B3s, because of the block and the ability to take them all the way through to NAD. Whereas the enzymes for taking NMN and NR into NAD are not going down with time. And then you'll see other people talk about blocking the enzymes that are draining off a lot of the NAD, and that's the CD38s, the PARPs, and the SARMs. And if they do use inhibitors, the NAD levels go up, and you get more, less aging in the animals that they do that on. But if PARPs are using NAD to fix my genes, I'd rather pour more NAD in and let them keep fixing my genes. Now, they do get hyperactivated, and there's sort of some excess use of them, but I'm not so sure about going too far down those pathways. And CD38, what's it doing? Using NAD to create tight junction integrity? I'm all for that. We'll just pour more NMN in. And so I bring up my keto slide just to remember we're going to talk about AMPK activation. Remember, this is that balance between fed and fasting. Keto before 6 is that not neutralizing factor, but it's an activating factor that moves you quickly into a fasting biochemical state without having fasted for several days or without having done carb restriction for several days. Matt was just giving us a story. He's been on keto before 6 and the keto diet for a couple of weeks, and he went to his vegetarian friend's house and ate nothing but potatoes and rice, and woke up in the morning and his blood ketones were 1.0. It kind of blew him away because this instantly fat adapts you and turns up all of the mechanisms for getting into ketosis. So AMPK activation, you've seen this lecture on that. So AMP arises when carbs are depleted, when exercise is depleted, AMPK. LKB1 is a pathway which you activate AMPK. That's more of a chemical pathway, and that's where metformin is working. That's also where the nutraceuticals are working. So AMPK activation, what does it do for us? It blocks mTOR, which is really good. So that's going to block protein synthesis and activate autophagy, which is that inward detoxification, going in and finding decrepit cells and regenerating them, decrepit mitochondria, that's called mitophagy, and digesting them in an autophagosome and then using the raw material to regenerate new parts. ATGC, that's adipose triglyceride lipase. That's increasing fatty acid catabolism while it's blocking ACC, which is fatty acid synthesis. These are all the aspects of the keto pathway. And in doing that, there's a couple things that activate that, the LKB1, this calcium enzyme, and of course you need AMPK. So there's a couple things that you got to do to activate that, all of which are accomplished by keto before 6, and it leads to all of these different effects. Now, we mentioned things like decreasing fatty acid synthesis, increasing fatty acid oxidation, but we didn't mention PGC1 alpha and mitochondrial biogenesis. This is one of the most important aspects of what we're trying to get through AMPK activation. Now, AMPK activation, you're going to see a lot of activity or a lot of talk around liver pathways, and liver health is totally dependent on AMPK activation and mTOR blocking so you can go into autophagy. The liver regenerates at a very, very rapid rate, and it's growing and growing and growing, and it deposits a lot of fat in there. And if you're not in this cycle between fasting and fed, you never go into this inward clarification. You don't burn up all those fatty deposits, and you create inflammation in the liver cells, leading to fatty liver and then to fibrosis. And so what are the things that are driving us towards fibrosis? Viral infections, fat accumulation, whether it's non-alcoholic fatty liver or alcoholic fatty liver, physical things like biliary obstruction, and carbon tetrachloride here is just all toxins, all right? And how do you drive that back? Adiponectin is created when you're fasting. Then you've got nutraceuticals like curcumin, anthocyanins. You've got pharmaceuticals like metformin or the nutraceutical berberine. It's nature's metformin, and there's some more pharmaceuticals. Now, I'd mentioned the tight junctions and the leaky liver, and this all happens when there's fatty accumulation. The hepatic stellate cells start accumulating lipids. They become activated, they become myofibroblasts, and they release NF-kappa beta and TGF beta, which then starts acting on the hepatocytes, damaging the hepatocytes through inflammatory mediators and creating a leaky liver. Now, AMPK blocks every one of these steps. All right. This is also happening at an immunological level, not just the myofibroblasts, but immune cells are creating inflammatory cytokines in different pathways that also lead to this leaky liver, but that's also blocked by AMPK. And once you get, I mean, sort of my view around this is once you start getting that leaky liver, then you start generating more fibrils of more collagen fibers to try to knit all that together, and that's the fibrosis. So turns out that that is all blocked through mTOR blocking, through AMPK activation. And this is a paper talking about long-term nutrient oversupply creating fatty liver and liver injury. And so mTOR blocking is super important. So AMPK tied together with sirtuins is super important to us. And then we see in things like milk thistle, the way that they fix things like non-alcoholic fatty livers, partly through AMPK and partly through sirtuins, raising NAD levels. Now, a lot of these, they're not, these are done in animal models where NAD is in adequate supply. So here we're just looking at all the ingredients. We're going to come back to using keto before 6 in concert with NAD Gold to get AMPK activation and sirtuin activation together for more of a cardiometabolic direction of the NAD Gold versus a longevity direction or an adrenal direction. So we'll discuss 3 different directions that we can take the NAD Gold. Here we have AMPK kinase, a therapeutic target in intestinal disease. And why? Because AMPK increases adherins, which make nice integrated tight junctions. And AMPK also blocks a lot of the immune hyperactivity that's going on right inside the GI. That's part of all your food reactivities. And what blocks AMPK? Endotoxin. All right. So AMPK is part of getting us back to a nice integrated tight junction. But we see a lot of that is driven not just by AMPK, but by the downstream NAD generation. So even if you're getting AMPK activation, but you don't have enough NAD, you might not get all of those effects on the tight junction. So here we have NAD ameliorates inflammation-induced epithelial barrier dysfunction. And so that's leaky gut. NAD blocking, blocking the initial formation of leaky gut. Speak through that. Those are doubled up. Okay, so why am I saying you might not get all the activity that you want out of AMPK activation if you don't have enough NAD? So if we look at this, one of the things we're looking for more than anything else is energy expenditure, which means that we need a nice, strong mitochondrial output. And that means we need a lot of mitochondria. Now, if we look at PGC1 alpha, so PGC1 alpha is the gene that's encoding for mitochondrial biogenesis, so we can make a lot of mitochondria. So first, we need to phosphorylate PGC1A, and that's part of AMPK activation. So AMPK, as it's activated, is first phosphorylated, and then it dumps the phosphoryl groups on the genes it's trying to activate. So that's taking PGC1A to phosphorylated PGC1A, but it's not yet all the way active. You need to take the acetyl group off to unsilence it, and to do that, you need a deacetylase. So what's the deacetylase? The sirtuin. And the sirtuin needs high NAD levels to activate and deacetylate the PGC1A so that the PGC1A can go and generate more mitochondria. Then you have the FOXO genes. We'll talk more of those about those over the next couple of years, but they're one of the other main age modulating genes, and they need to be deacetylated by sirtuins too. And indeed, you look at that and you say fasting, exercise, take out metformin and put in our nutraceuticals like keto B46, there's a chance they won't take you all the way there if something's drawing off your NAD. They will help generate more NAD, but if you can just go in and bump that NAD level, you are sure to get all of the benefits here. And in fact, you look at this paper, requirement of NAD and Sirtuin activation for lifespan extension by caloric restriction. Which means if you don't have NAD, your caloric restriction is not going to lead to lifespan extension. So AMPK needs high NAD for all the benefits. But the next step in this puzzle is NAD needs to be balanced with methylation. There's a really cool paper that you can find online, Nicotinamide, NADPH, and methyl group homeostasis evolved and became a determinant of aging. So these guys are looking over time at different civilizations that either had high or low niacin, leading to high or low NAD, and then whether they had enough methylation groups in there. And there are different things that activate the methyltransferase that drains off the nicotinamides and lowers NAD activity. So they say high NNMNT activities linked to Parkinson's, cancer, and diseases of affluence. Optimizing nicotinamide and choline methyl group availability is important for brain development and increased during our evolutions, raising metabolic and methylome ceiling. So as we got access to both of these things, we were able to raise our potential. So NAD builders must be balanced with methyl donors for optimum health. And they have this graph where they're talking about neonatal. If you have low NAD during your formation, well, then the outlook is piss poor, you're kind of screwed. If you have good when you're being formed, then you have good brain development. And then when you go on to post neonatal, if you have low niacin over time, you move towards a dementia-like brain issue. Whereas in excess, with not enough methylation, you move towards a classical Parkinson's symptom type presentation. So they're saying you need this balance there. And so they continue to say accumulating evidence points towards the probability that aging diseases such as Alzheimer's, Parkinson's, cancers, metabolic diseases originate in mitochondrial depolarizations and uncoupling. Remember, that's the uncoupling between the nuclear and the mitochondrial transcription of their subunits for oxidative phosphorylation, with disturbed electron-proton flows as proteinopathies. You don't have that proton flow, creating ATP. A unifying explanation imagines abnormally spreading metabolic fields if the challenges of balancing NADH-dependent energy supply and demand with the need for optimal methyl group availability. So you have to balance both of those together. And in fact, they've seen that excess activity of the methylation genes contributes to the development of fatty liver. So when you don't have enough methyl groups, because NNMT is driving off the methyl groups, it will lead to low NAD, which will lead to fatty liver, and it'll lead to low methyl production. All right, so we need, as we raise the NAD levels, there's going to be more formation of nicotinamide. Nicotinamide needs to be moved out of the system by methylating it. So you need the methyl to move it out. Remember, if you build up the nicotinamide, you block the sirtuin. So you only get some of the activity of the NAD. All right. So we balance that we do have TMG in the NAD gold. So the NAD gold is a 1-to-1 blend of the nicotinamide mononucleotide with the TMG, but for a lot of people, they need a little bit extra methylation. So I need extra methylation, whereas Mindy over there does not. Ashley probably needs triple methylation. So TMG is one of the ways to do this. You can take 2 to 5 grams of TMG. TMG is a nice, easy way to build methylation without being too top heavy. By top heavy, I mean if you're going to the top of the methyl chain and using like methylfolate, you easily can disturb your mental condition and go from depressed to manic in a heartbeat. Whereas TMG is not going to do that, but it's going to give you all the methyl donor groups that you need. Now, B2 is really a great way to turn over the movement of the methyl groups. In fact, they're finding that a lot of the MTHFR issues can be solved by supplementing B2, because B2 drives the methyltransferases that enable you to move the methyl groups around. It's not like you're like seriously deficient in methyl groups. You often just can't move them around fast enough. Now, what we've been doing, because I started doing this all with betaine, and then I moved into using the liposomal B12, and I found that that works really, really well. So for every 2 pumps of the NAD Gold, those 2 pumps will give you 50 milligrams of NMN. You do 1 pump of the methyl B12. That's 500 micrograms of methyl B12. So I do them in a 2-to-1 ratio, and that works for most people. Only the extreme undermethylators will need more, and really good methylators won't need so much, but it's it's not going to turn them sideways. Now you can be tracking homocysteine as a marker of this, but a really easy way to get to tell, if you take NAD Gold and it doesn't give you energy, or it might even give you fatigue, then you need more methyl groups. Now I will say, the first time you take it, you may go and take a nap as your body resets itself. There is some early stage dosing of this where the whole body resets. That's a little different. But if you're taking it, so like my friend Avi Hershkowitz, he was taking it, he's like, I don't know, I'm getting a little fatigued. And I said, dude, I told you need more methyl groups. And so he added in the methyl B12, and then he's like, oh my God, I feel great all day long. And he says, this is probably a better test of methylation capacity than doing homocysteine. You take it, you're tired, you need more methyl groups, take it with the B12, and you'll see you come right back. All right, so how do we raise NAD? Obviously with NAD Gold. All right, good. All right, so just to bring it back to nicotinamide and nicotinic acid, remember the enzymes that drive them all the way to NMN go down with age, and they go down with inflammation and other biochemical stressors. So you can push those in, and sometimes you won't get them all the way to NAD. The niacin will just cause flushing, and the nicotinamide will just cause blocking of your sirtuins. Because remember, it's the inhibitor of the sirtuin. And high NAM buildup upregulates the NNMT. So NRK, which takes nicotinamide riboside to NMN, and NMNAT, which takes NMN to NAD, they don't get down-regulated with age and stress. So previously it was said you had to use NR. Like I said, oh, it's the only thing that gets transported around. But hey, this last February, a little less than 1 year ago, it was discovered. Here it is from our good Japanese friend, Shinichiro Imai. The SLC12A8 is a nicotinamide mononucleotide transporter. It is in the GI tract. It is in all the cells. So you can transport this stuff all through the body. And then here is Sinclair singing the praises of the paper, saying the elusive NMN transporter is found. All right, great. So it's been established we can use NMN. In fact, Sinclair was using NMN in animal studies, so he knew it had to work, but nobody had the mechanism. All right, so it works. What are we going to do to it? We're going to put it in a liposome. That's what I want to hear. And the choir sings, put it in a liposome. And that's what we're going to do, because that's what we do, because we create bioavailability. That's our job. That's our game. Oh, look. And so this is Mindy's slide. I didn't know it was going to do the rotating thing, She didn't either. Oh, what a pleasure. All right, so you know that we make liposomes, which have a water core, and nanoemulsions, which have a lipid core. So keto B46, those are all fat soluble compounds. They go into a nanoemulsion. It's got a little oil core, and they're all in there, surrounded by phospholipids. Now, water soluble like NAD or NMN or B12, they are going to go in a liposome, which has a water core. And we've taught again and again and again that size matters. To make these things work, you have to get down to really small sizes. In fact, liposomes were discovered in 1964, and they've never really made it into commercial use except in cosmetics in the 80s until recently, because they were never increasing oral bioavailability, because they were making them by these old methods and they were really big liposomes. So you've got these multilamellar vesicles in the 300 to 5,000 nanometer range, these ones that look like milk in the 1 to 300, those are large unilamellars, then the small unilamellar vesicles in the 20 to 100 nanometer range. And the smaller they are, the faster they absorb. And so this was an uptake study from the literature done over at NIST, and you see as you go from 236 nanometers down to 50 nanometers, I think there was a 64-fold increase in bioavailability. It's a really big thing. You have to be really, really small. Remember Steve Martin, get really, really small. And what does it look like when you're small versus big? When you're big, you look all cloudy, and this milky stuff is a classic one. These are different CBD emulsions and liposomes, and they're all pretty unstable, and they're all really large, and they all have poor bioavailability. This one is 25 nanometers. You see it's crystal clear. You can see right through it. Why? There's particles in all of these. There's about the same lipid concentration in all of them. But in that 25 nanometer, the lipid particles are smaller than wavelengths of light, so light goes through, it does not refract and pop back. This is really nice because you can just pour something out and look at it. You don't need all my laser sizes. I got laser sizes all over the place because we want to know, is it 25 or is it 35? Because we're the only company that actually puts it into the specification that it's got to be a specific size. And we've seen again and again, the smaller it is, the better the uptake. In fact, in Keto B46, all the R&D samples that we did all the research on were in the mid to upper 20 nanometer range, and we went up to production. They used a slightly different ingredient for one of the membrane components. The size went up to 70 nanometers, and it only worked like 40% of the time. We fixed it, used the right ingredient, brought it down to the upper 20s, works 10 times out of 10, like Shaft. Who comes through 10 times out of 10? I'm so glad I got to use that clip in a webinar. All right, so what do you get when you use nanoparticles? You've seen over on the bottom left, we have this CBD uptake study. Well, we finally got this was measured over at CU Children's Hospital over in Denver, and we got all the equipment inside it. We got to reevaluate all these points. All of them were the same except this point here. Here's the new data set. Look at that. That's the way it's supposed to be. 25-minute peak. The guys at CSU that are doing resveratrol particles are finding a 15-minute peak. So the immediacy, a big whopping dose into the blood between 15 and 30 minutes, and then you have it coming down from there. So this is a 6x increase in bioavailability from the lipid nanoparticle. And there's just electron microscopy of those lipid nanoparticles. We've done, and that was a blood uptake study. One of the ones when it's harder to measure the compound in the blood, like glutathione is, like NAD is, we'll do a CACO2 study. CACO2 is you grow out cells, intestinal cells, on a membrane between two compartments, and you load your compound in there and you watch how fast it goes across. So we put the liposomes in the top and we measure them going through. This is a measure of bioavailability. So here's our glutathione versus all the competitors, and the green line is the control. So you always want to beat the control. And the farther you beat the control by, the higher the increase in bioavailability. All the competitors were as good as the control or even significantly worse. What did we get with the NMN? We got a 4.25x increase in bioavailability over raw NMN. So if people are saying, well, 300 milligrams of NR or NMN per day is great, well, now you have to take, you can get the same effects taking 1/4 of that. So do I take 1/4 of that? No, I still take a lot, and I get a lot more in. So what do I take per day? I take 100 milligrams a day. And then on big days, I'll take 200, maybe 300 milligrams a day, and multiply that by 4.25, and you have how much is getting in there. So intro doses will be 2 pumps, 50 milligrams a day. Do that for a little bit, then move up to 100 milligrams a day. All right, so what are the different ways that we're going to blend together different supplements? Here's our cardiometabolic blend. This is using AMPK activation through KetoB46, and we don't have time to go through this, but the right AMPK activation, you need a number of different compounds to hit all the different things that upregulate AMPK, and KetoB46 has all those elements in it to get that strong AMPK activation. Then you're going to get the NAD in through NAD Gold, and you're going to balance it with some methyl support. So a teaspoon of KetoB46, 2 to 4 pumps a day NAD Gold, 1 to 2 pumps of the methyl B12. Now with this one, because KetoB46 activates so many liver pathways, if you're taking that right out of the blue, you might need binders in the beginning for the first week or two. So follow it a half hour later with some ultra binder. Skip through that. Oh, incorporate that with some intermittent fasting and you are there. You take all that stuff in the middle, in the morning, don't eat any carbs. Maybe you'll have a bulletproof coffee a half hour later, but that's about it. And wait until you eat lunch. Maybe, you want to get like a 16-hour window where you're not eating anything at all. So you couple intermittent fasting with that AMPK activation, you'll have fantastic results. Now, the Sirtuin activation blend, and here's Guarente saying that thus combination of Sirtuin activation and NAD intermediate supplementation may be an effective anti-aging intervention, providing hope to aging societies worldwide. Worldwide aging societies, all going to be happy that we're going to give them this. Here's our Sirtuin activating NAD or Sirtuin and NAD activating blend. 1 teaspoon of the one, you've got resveratrol, PQQ, CoQ10, phosphatidylcholine, and adaptogen. So you've got some things that are providing adrenal support, membrane support, Sirtuin activation, and CoQ10 all together. And then you're bringing in 4 pumps or 100 milligrams of NAD Gold and 2 pumps of the methyl B12. And that one's really awesome. So I call that the Angèle protocol. Angèle is my mother-in-law. She came over for 6 weeks over Christmas, and when she gets here, last year we were giving her the one, and it really changed her a lot, but not like this. When she got here, she could walk about 20 feet before being absolutely too winded to do anything else. After a couple of weeks of this, like within really just a week, she was walking the lake behind us. It's a 1-mile track with the dog. After a month, she was walking it twice a day. I mean, it was really, really incredible what that did for her. Last one, adrenal recovery blend.
Yeah. The other one is called the Energy and Longevity Bundle on our site.
This on our site is called the Energy and Longevity Bundle. I thought you were just beating me up to keep going and get to the questions. But yeah, because this is so great, and I love this protocol so much, we put it together as the Energy and Longevity Bundle. Adrenal recovery. Now, when I first got the NMN, the NAD Gold, I fixed my adrenals in no time. Now, with the adrenal recovery, and if in the beginning you're getting more of a fogginess and the methyl groups aren't quite cutting it, you're turning up mitochondrial activity. There's a lot of free radical activity, and until the whole system has caught up, you need a little bit of free radical control, free radical stabilization. And so we're going to bring in some antioxidants, and that could be glutathione or vitamin C or both. One thing that vitamin C has is it's also a histamine catabolizer, so it's helping break down histamines. Then you're going to need the NAD. Keep it on the lower level when you have adrenal fatigue. Just start with 2 pumps, or go then 2 pumps twice a day. Don't put the whole 4-pump blend in right away. B complex. Now, you might ask, why didn't I use B complex for the methylation? It says methyl B complex, but the methyl B complex also has nicotinic acid and nicotinamide. It's not quite pro-methylation enough to balance on its own, but it's got things for the adrenals like the B5 that are super important. So you'll end up taking an antioxidant. I took glutathione, I took methyl B complex, I took NAD Gold, a little extra B12, and then I backed it with some adaptogens, and I used the one. Now the one is also going to bring in the Sirtuin activating activity. So you take that energy bundle, the one, NAD Gold, and methyl B12, and your adrenal depleted, just add in a little B complex and one or both of these antioxidants, and you'll bring that back up very, very quickly. Neuroinflammation, take that same energy and longevity blend, add in CBD and glutathione for fixing brain activity. All right, so that's it. We're going to take some questions, and I will show you the webinar special offer while I take the questions.
And there's quite a few of them, so
Quite a
to
few.
get
All
through
right.
as many as possible. Okay. First, how does liposomal NMN compare to IV NAD?
Well, they're a little bit different. So IV NAD is a whoop, really quick. They have to do it really slow because it catalyzes so many functions so quickly. And of course, every time that something like, feels really weird, oh, you must be herxing. Well, no, it's such a fast shift over to the B3. A lot of the undermethylators really had a hard time with that. It also winds up liver activity really quick. So it needs to go in a little bit slower and needs to be coupled to other things if you're having a hard time with it. This is more of a steady thing. We're going to build it day by day by day by day. I always talk about IVs as punctuating something. You get this peak that you can't get anywhere else, and that causes a lot of very beneficial changes, but it's the day-to-day building of your reservoir of NAD that I think is a more important thing to do, but I do like seeing you do both.
And how would you go about starting NAD? Would you titrate up? Would you start with the higher dose, a loading dose, and go down? Should you pulse it?
No, that's a great question. A loading dose might be, it's just like the IVs. It might work for some people, but some people it might destabilize them going in too quick. So I would titrate up. I like starting with 2 pumps and whatever else you need to balance with it, seeing how you're doing, a couple days like that. Then go up to 4 pumps. Matt and Dale, our clinical guys, are like, yeah, we've been doing 2 for like a year now. We're ready to go to 4. Mindy and I were like, "Wuss, man, we've been at 4, 10 times a day for the last month." Or at least once a day. But Mindy and I, we were shaming them for not titrating up faster. But, I will say, that under a lot of pressure, you go to multiple doses a day, but 4 once a day has been really solid. And it's not like, oh, now I need more. I mean, it's just been a steady cruise. And it brings together the adrenal function, which is not just to wake you up, but there's so much free radical control. The glucocorticosteroids are coming out with the adrenals. Like, you wake up and you drink that coffee and you get foggier. That's because the adrenals, instead of just putting out energy and free radical control, they can't keep up with it anymore. And the pro-inflammatories are beating out the anti-inflammatories. And when you get those NAD levels up, that balance between the immune, the adrenals, and the mitochondria, it just locks together, and you've got energy steady all day.
And back to the discussion of nicotinamide riboside versus NMN. How do you differentiate the 2 products from a pathway standpoint, converting those 2 precursors into NAD?
Yeah, so NR becomes NMN, which then becomes NAD. So from that standpoint, now you only have one enzyme to take it from NMN to NAD. You don't have the NR to NMN. Does that functionally matter? I don't know. Cremedex claims to have some data saying that NR worked better than NMN, but then you take the liposome and you got 4.5x increase in absorption. The NMN is then it's got to be outpacing the NR. But we'll be running tests looking at all that and how much NAD production capacity you're getting at each dosage. What's the equivalent? Like, if you're taking 300 milligrams of NR, how much of this is exactly equivalent, and how much is above that?
If you are just following a regular diet, can you get enough NAD precursors and Sirtuin activators from food in order to significantly, stop the aging process?
No.
Yeah.
It's taking them from, those vitamin forms, the nicotinic acid or nicotinamide, all the way through. It just becomes harder and harder with age. And coming in with these higher precursors, they cost more, but they spin right into NAD very, very quickly. And from diet, getting enough Sirtuin activators to get this, That's a lot of red wine.
That's right. Kind of focusing on keto before 6 for a second. Do you actually have to follow a keto diet to get the AMPK blocking benefits from keto before 6?
Yeah, the easiest way to go with keto before 6 is just intermittent fasting. So give it the morning. You take that in the morning, hour and a half, 2 hours later, you've got blood ketones. And you'll be in ketosis until you eat lunch. Now, what are you going to eat for lunch? You eat a salad with some salad dressing and a little protein on there, you're still going to be in ketosis. You eat a big thing of pasta, it'll probably block that. But, just being in ketosis for a couple hours a day, I think is really going to be a good thing. Even if you're taking it with a carb-heavy diet, it's going to increase how effectively you burn up all that stuff. At its best, it's making you burn both pathways at the same time. It's increasing glucose transporters into the cell. It's increasing breakdown of glycogen instead of formation of glycogen. It's increasing breakdown of fat instead of the storage of fat. And when I was meeting with my friend Elena Gross in Europe, she's an Oxford PhD, and I forget her friend's name, who's her chief medical officer. He's also an Oxford PhD on these pathways, on ketosis. They said the golden, the golden goblet is when you're burning both at the same time. And from the data I was showing her from the keto before 6, she said it looks like you're getting both those going at the same time. Your blood sugar's 100 and your ketones are 1.4. You're obviously doing both. You don't have to sink to 70 and then the ketones pick up.
Okay, so with NAD Gold, we have, the TMG in there, and we have solutions for people who need additional methylation support. Yep. What about if you're an over-methylator? Should you be concerned about using NAD Gold, or is there anything else you can do?
No, I think you'll be fine with NAD Gold. If you're an over-methylator, you're not going to add in the methyl B12. If you're trying to do adrenal stuff, maybe get a totally non-methylated B complex, or at least just B5, but that's sort of like a base blend, and it's not going to over methylate people, but it gives you a little bit of TMG to go with it.
So do we need to be careful with autoimmune patients with upregulated immune system in any way from this product?
Yeah, I don't think so. I mean, there's fears around using it with cancer, that the cancer cells drive on NAD. And so I'd like to get, real strong pathologies dealt with before you build this up, or real strong toxicities. Start working on those before you build these up. I don't see the autoimmune problem because it's not an immune activator, it's an immune balancer.
So we have a whole bunch of questions around detoxification, mercury detoxification, our protocols. So first, for something like the push catch, how would you incorporate this product into that protocol?
Yeah, so we were talking about the 1, NAD, and B12. With push catch, just put liver sauce in there. And so liver sauce, a teaspoon of liver sauce, start with 2 pumps of the NAD Gold and maybe 1 of the B12, and do it that way. Like in the mold protocol that we just released with Jill Carnahan, the mold box, that incorporates NAD Gold into it at that ratio of, I think it's a teaspoon, maybe it's a half teaspoon of liver sauce, and then 2 pumps of NAD Gold. So you can add it in when you're taking the liver stuff, and that'll add more energy in all those liver pathways.
So any protocol that has the push portion, the liver sauce, or the bitters, you would combine the NAD and the B12.
Yeah, exactly. While you're taking your liposomes, you're just going to tack these guys right on top.
Okay. So around mercury, for someone who is already toxic with mercury, will this help to reduce mercury damage, or can you really negate that when pre-treating with NAD prior to amalgam removal, or whatever caused the damage?
No, you're going to build up. I mean, this whole thing in the way we go after mercury and detoxification is we want to build up the body's resistance. And part of that is depuration. It's moving mercury out, but it's making the cells more resistant at the same time. So it's not going to, you know, there may have been damage already, and it's going to help you accommodate that damage and regenerate from that damage, but it's going to make you less susceptible to the mercury that's still in your system, and it's going to turn up the drivers that are moving it out of the system. So I would advocate for using this in those cases.
And for amalgam removal, how would you use NAD Gold to protect against that?
Yeah, well, I would start with, you know, if you're building up to the amalgam removal, start with, you know, 2 pumps NAD, 1 pump methyl B12. Now, the thing is, are you going to build the whole push catch into there to deliver sauce glutathione? I would at least do liposomal glutathione, NAD Gold, and the B12, and, you know, go on that once a day for a week, twice a day for a week, and then go into your revision. So you're getting your body ready. Here I'm doing the Angel cocktail. Teaspoon of the one.
Okay. And I think we have time for one more. Do you have any thoughts around pregnant patients using this, or
Talk to your doctor.
or could it be helpful with autistic children?
Oh, yeah. I mean, we're just getting to where we're going to start. You know, usually we get this all integrated into our own systems, and then we talk to our autism practitioners. And I was just talking this morning about, you know, one of the kids that I've watched for a long time, and I'm like, oh yeah, I think it's time for him. So especially those kids that are really mitochondrial damaged children, I think that this will be a game changer. I mean, a lot of them, they did really well with the one. You'd start detoxifying them, then you bring in the one, and that brought them up to a higher level. Now you bring in the NAD, I think it'll bring it up to an even higher level. I'm very excited to see that. There, the balance of the methylation and the NAD is going to be real crucial, and so they'll have to watch that. But I'm very excited to bring this into the autism community next.
Great. And there have been a couple questions about antidepressants and those patients taking NAD. Should there be any contraindications with that?
I can't speak too deeply to that. I don't think so. I mean, it definitely increases your mood, stabilizes your mood quite a bit. You know, into the specifics of an interaction with it's going to come down to that methyl balance. And in depression, there's usually a low methylation status versus high methylation. You know, the over-methylators are more the manic ones, and the depressive ones are the under-methylators. So, you know, maybe it's going to be 3 to, maybe it'll be 1 to 1. Mm-hmm. So you just have to watch the methylation status when you bring the NAD in.
Gotcha. Okay, and that wraps it up. So
all right.
So we'll be sending out the recording of this webinar along with the promotion specific to this presentation.
Which I have up there, 20% off NAD Gold, code NAD webinar, all one word, any quantity, 30 or 50 ml sizes. And so we have the 50 ml size, which has a retail of what? 90? I don't know. We'll find out in a second. We have a 50 ml size and a 30 ml size.
45 wholesale, 90 retail.
Yeah, so 90 retail for the 50 ml and 60 for the 30 ml. And so there is that a little bit easier to get into it with the 30 ml. All right, so thank you very much. Thanks for staying 15 minutes late. There was a lot of stuff to cover in that webinar. And we will see you on our next webinar sometime next month. I don't know what we'll be covering, but we'll be covering something. Do you know?
Yeah, mold toxicity.
Oh, mold toxicity. So we're going to have Jill here?
Yeah.
All right, so it's going to be
chatting to her.
What's that?
You better get talking to her.
Yeah, I better talk to her. It's going to be me and Jill Carnahan. We'll do it together live, and we'll cover Jill's mold box. And that will be a super exciting one too. So thank you guys so much, and we'll see you next time on Quicksilver Radio.
Okay, it's ended.